infinitely long wire. So what do we mean by that? I'll just tell you what do I mean by infinitely long wire and uniformly charged. Okay, so this is the application of Gauss's law. I think, yeah, you can see that. So infinitely long wire and uniformly charged wire. So we'll see what is that infinite means. Infinite means your wire is really very long. Suppose 2 kilometers, 3 kilometers, 4 kilometers, 10 kilometers, whatever. So infinitely long wire. So that kind of long wire. In general, in our laboratory, we take few centimeter, at the most few meter. But when it talk infinitely long, so 10 kilometer will be an infinite wire. Okay, infinitely long wire. Okay. Now uniformly charged means what? Suppose this. Uh, so wires generally has to be little bit having the symmetry, cylindrical symmetry. So this is the wire. Uniformly charged means the charge density will be the same. Okay, if I take any portion of it, okay, any portion of it, it will be having the same charge density. And this has, see, this is actually line, right? This is a conductor line. Okay, some wire means line. Okay, so which uh charge density, which kind of charge density should we take for this nickel? There are three charge densities, right? One is line charge density, denoted by lambda. Okay, line charge density. Then we have surface charge density. Okay, so which is denoted by sigma, and we have volume charge density. So among these, which we should have used, which we will be using here? This is denoted by rho. So line means you can see it's we'll be using line charge density, right? Lambda. So this line charge density is same for whole the wire. So this is called uniform. Okay. So uniform and infinite. These two words, I hope you have understood. These two words you have understood, right? So now we'll see. We have to find out the electric field for see infinitely long wire. That's why they have given dot dot dot. Okay, both sides, so it can go up to infinity. Now we have to find out electric field for this. So applying Gauss's law. So like Gauss's law is this E dot ds. This is the left hand side part, and right hand side is 1 by epsilon naught into charge enclosed. Okay. So what we have to do, we have to calculate electric field, and for that actually what we have to find out, we have to find out the flux. This is called total flux. Okay, and flux through what we have to find out? Flux to the Gaussian surface. That day I talked about Gaussian surface. So for anything, if we want to calculate electric field, first of all, what we have to draw? We have to draw a Gaussian surface. What we have to draw? We have to draw a Gaussian surface. But how do you draw a Gaussian surface? That depends on the symmetry. Like which shape the Gaussian surface should be. Whether it will be a cylindrical Gaussian surface, whether it will be a spherical Gaussian surface, or whether it will be a planar Gaussian surface. So what it is? So that depends on the symmetry of the problem. Symmetry of the problem here. What is the symmetry it has? Whether planar symmetry, or whether cylindrical symmetry, or line symmetry. That we have to determine first. Okay, to draw the Gaussian surface. So what will be my first step to apply Gauss's law? Draw Gaussian surface. First will be that. Okay, Gaussian surface. So for that we need to know symmetry, right? Symmetry of the charge distribution. What is the symmetry of the charge distribution here? Whether it is cylindrical, whether it is spherical, or whether it is planar. What is that? Which symmetry does it have? How do you understand here? Look here, if I have an wire, if I think I have to find out electric field over here such a certain distance r, and so from the wire itself, so from the wire, so from anywhere you take any distance you take from where up to r. So so suppose my point was sometime my point was here at P. Now if I just rotate this point, okay, throughout the, so making like in a circular path, making like surrounding this wire, okay, I get a circular space, and then if I just move forward also to cover the whole wire, like that, so I'll just rotate and then move forward, rotate and move forward, so you will get concentric uh, circles like this. If you just add them, all of them, look that. So I think these are will be so all having the same radius. Okay, like they. Okay, so I'll just I think I'll draw it again properly. So if you draw circles like this and just move little bit and then draw here again and move little bit, draw here again. So you will get a cylindrical symmetry. You'll get a cylindrical symmetry, isn't it? To cover the whole uh, wire, you will get cylinder, okay, infinitely long cylinder. Understand? Around it, like this. So if you just understood what I'm trying to say, why we should take what kind of symmetry we should take for this linear charge density to draw the Gaussian surface, or yeah, Gaussian surface, we have to take cylindrical symmetry. Do you understand, Nikhil? Why do we take Gaussian cylindrical symmetry over here? And we will be drawing a cylindrical Gaussian surface around the wire. We will be drawing a cylindrical Gaussian surface around the wire. And suppose I have to calculate electric field at certain distance r at P. See, at this point P. So, yeah, Priyadarshini, do you understand why do we take cylindrical symmetry? Do you understand that? Just let me clear this. Why do we take cylindrical symmetry for this wire? Do you understand that?
Yes, sir.
So first what we'll do, we'll draw the Gaussian surface. We'll draw the Gaussian surface that through the point at which we have to calculate the electric field. So suppose they have asked you to find out the electric field for an infinitely long wire, infinitely long, uniformly charged wire. Okay, uniformly charged wire. Charged wire. So to calculate the electric field at any distance r, or at any point P which is r distance away from the infinitely long wire, first of all you have to draw a Gaussian surface, and that surface is actually of cylindrical shape, because this wire has a cylindrical symmetry. As I said, if you just make a circle of radius small r through the point which you want to calculate the electric field and just move away, then do the same thing, okay, and go like that, so you'll get a cylindrical symmetry like this. Okay, you'll get a cylinder. So that's why you have to draw a cylinder. Okay, you have to draw a cylinder through the point you have to calculate the electric field for this wire. And see, for the time being, I am just showing you, see this one. In this figure you look here, you might be thinking, sir, that is very fine, we'll take a cylindrical surface, but how long we should have taken? For the infinitely long we have to take? We'll answer it here. You look here. So we don't have to take infinitely long wire. We'll just take a like finite length of L, and then we can generalize that formula. Okay, generalize for infinite length. In fact, we will see there will be no length term in the electric field itself. So length does not matter at all. So only thing is mattering is actually the distance from the wire and the charge density, that we will see here. So in this case, then we have drawn the Gaussian surface as a cylindrical symmetry. This one we have drawn. This is the Gaussian surface. Okay, the dotted line. This is cylinder. Okay, through the point R. Look here, through the point R. So the P they have taken here in the Gaussian surface. I might have taken this here only. Okay. Now what you have to do? After doing this, I'll just clean all. So first draw Gaussian surface. So Gaussian surface we have drawn. Okay. Then second thing, what you have to do? You have to calculate the total flux through the Gaussian surface. Okay. First of all, you find out what is the angle between this electric field and the area normal. Okay. This is the area vector. That means the area normal, right? So in this case, you have to see. So which direction the electric field is directing? See, cylinder has a nice symmetry, radial. See, electric field for this wire will be having actually radial symmetry. That means the electric field will be always in the radial direction, always in radial outward. See, radial direction means at this point electric field will be like this. Okay, okay. At this point, this is radially outward. You might be thinking, sir, how do you say this electric field will be radially outward? I'll tell you why. If I take, see, if I take two patches of the wire, so suppose this has certain length dl and it has certain, okay, so this has certain charge density lambda. This wire has charge density lambda. So total charge will be lambda into dl one, and here another patch equal length. This also may be lambda into delta L1. So if I try to calculate electric field at this point for these two like small elemental length of the wire, look what will happen. So see, it will make, see, electric field always will be outward, right? See, this is a positive charge, so it will be going out. So always from the positive charge it will be like this electric field. So the electric field direction at this point due to this P2 will be in this direction. Look, this is the direction. So this is actually the electric field for P2. And see, the electric field for this patch here at this will be actually EP1. And see, it has actually uh, certain angles. See, both of them are actually of from the same amount of charge, lambda del 1 d1. Okay, del L1. Okay, so they will be having equal magnitude as we have done from the dielectric case, dipole case also. In this case, look, these two guys will be having the same value of the electric field because I have taken the same length of this part. If P2 and P1 are of the same length. Now if I just take the component of this field and this field, see the vertical component, they will be actually cancelling each other. Vertical component will be cancelling each other. So what will be remaining is this component. Okay, this is the component which is actually along the radius of this circle. Okay, the circular plane. Okay, this, so this will be actually, so do you understand, electric field will be only along the radial direction. Okay, only along the radial direction. So the along the length of the wire, along the length of the wire there will be no electric field. See, electric field along the length of the wire will be zero. So this you have to understand properly. Okay, to find out this flux, total flux, we have to first find out what is the direction. the of the electric field and which are the surfaces I am going to take for calculating the total flux through. So first we have to draw the Gaussian surface, then we have to find out the total flux through the Gaussian surface, through the Gaussian surface. Now I'll show you. See, so we have taken the electric field to be radial direction. So what will be the flux through this way? Flux through this way will be 0, right? Because see, the ds is actually ds normal of the area would be in this way, and electric field is this way. So 90 angle between this uh, angle between ds and electric field, that will be 90 degrees. So cos 90 here it will be given 0. Similarly, flux through this surface also, see, if this is this way, so there will be 90-degree angle. So flux also here will be 0. So the flux through the flat surface will be 0. Do you understand this fact? Nikhil, you have to respond to my question. Do you understand
Yes,
why
sir.
the electric flux through the flat surfaces are 0? Do you understand that? I hope you understand this. Priyodashini, you also understand, right? So the only flux
Yes,
we
sir.
will be having, so flux, yeah, so flux will be through only through the this curved surface, okay? So how do I write electric flux then? And see, in the curved surface, what is the area normal? What is the normal to the surface in this case? In this direction only. What is the electric field here? In this direction also only. So E and see, E, the electric field and the normal of the area are in the same direction. So this will give you EDS. EDS. Okay. Now I have got EDS. That is very nice. Now see, we have to see whether this electric field is varying or it is constant. Okay, this is varying electric field or constant. See, at this particular point, if you just take like a point P prime, see P prime here, this is also from r distance away. So since it is electric field radial, it will depend only on the radial distance. That means around this circle, okay, circular path, or on the curved path of same radius. See, r radius away, the electric field will be same everywhere. See that p prime distance also, this is r, this is r. Even if I take another point here, so this also having r distance from the wires. So the electric field will be constant throughout this curved surface. Do you understand that? Electric field will be constant throughout this curved surface. So it does not depend on, see, it does not depend on the length. Do you understand that? Now you understand it does not depend. Electric field does not depend on the length. It depends on the length of the wire. It depends only on the radial distance. If I draw another, see, if I would have drawn another cylindrical surface, so in that case actually radial distance is different. So electric field will be different for that case. Okay, electric field at this point will be different than this because they are at different radial distance. Okay, so now I hope you understand that we can we can take this, since this electric field is constant throughout this curved surface, we can take this electric field out of the integration. Okay, then I have to find out what is the surface area of this Gaussian surface what we have drawn here. The Gaussian surface area of this Gaussian surface of length L. What will be the Gaussian surface, like surface area of this curved surface of this cylinder? 2 pi 2 pi r into
2
L.
pi
L
RL.
is the length of the cylinder, right? Right. So we will get the flux. So this integration will be 2 pi RL. RL. So this will be 2 pi RL. So you have got the total flux now, right? I'll just remove everything. So first we had drawn we had drawn the Gaussian surface. This is this one that depends on the symmetry of the charge distribution, which was line charge density. So we had to take cylindrical symmetry. Then second point, we had to calculate the total flux through the Gaussian surface. Now from the through the flat surface electric flux will be 0. So only flux we have to calculate through the curved surface which we have already calculated. So that is what 2 pi into 2 pi small r into L. This is the total flux through the Gaussian surface. And according to Gauss's law, this will be equal to charge enclosed divided by epsilon naught. Okay, this is the Gauss's law. Now you might be thinking, so what is this charge enclosed here? Charge enclosed means in charge enclosed by the Gaussian surface itself. Charge enclosed by the Gaussian surface. So what is the charge density here? Lambda. So lambda, what is the total charge then for this Gaussian surface enclosed by this Gaussian surface? This is the line charge density. I have to multiply the length of the cylinder. So you will get charge enclosed lambda into L. Do you understand this? How do I calculate the total charge density? Charge enclosed by the Gaussian surface. So it has actually line charge density. So you have to multiply the length with the line charge density lambda so that you get the charge enclosed. So this length we don't have to put infinite length because charge enclosed by the Gaussian surface we are calculating. So this is not infinite. This is the length of the cylinder. Okay, length of the cylinder. Understood why length of the cylinder? Because we are calculating the charge enclosed by the Gaussian surface. So ultimately what you will get is the left hand side the total flux through the Gaussian surface is 2 pi RL, and on the right hand side charge enclosed is lambda into L divided by epsilon naught. Now L goes up from both sides, so what we get is actually lambda by 2 pi epsilon naught R. So this is the electric field. This is the electric field due to this infinitely long wire. Due to this infinitely long wire at any distance r from the wire. At any distance r. So it is, see, at this point electric field is same as electric field here at r distance. Okay, if this is the r distance, electric field here at r distance is the same. So see, it depends on the radial distance from the wire, but it does not depend on the length. Does it depend on the length? Electric field does not depend on the length. It depends on the radial distance from the wire. So this is the electric field due to infinitely long wire. Okay, infinitely long wire and uniformly charged. Obviously, uniformly charged. And since it is a line charge, we have taken line charge density lambda. This is all. See, this is actually written. Whatever I have told, this is elaborately written in your book. Okay, if you read very carefully, I have spoken each and every word. Okay, one more point I just forgot. Since it was positive charge density, see, I have taken as a positive charge density lambda positive. So lambda. So see, what will happen if the charge density is negative? Now we'll try to draw the electric field from the wire itself. Let us see. So the electric field from this wire, it will be like this. So if this is the wire positive charge density, okay, so electric field will be like this. In this way it will be, okay, like this. Okay, it will be radially outward. But suppose the charge density is not positive, this is negative charge, negatively charged. So then what will happen? The electric field lines, how it they will be coming like this. Okay, okay, they will be coming into the wire. Okay, like this. This will be electric field direction. Okay, this is how. So if it is lambda, electric field will be lambda is negative. So you can have positive or negative lambda. That doesn't matter. Okay, that depends on the charge density, whether it is positive charge density or negative charge density. So according to that, you have to give the direction, inward or outward. So this in vectorial form, what I can write this electric field is, see, in this case positive, right? So I'll be writing 2 pi epsilon naught here r into r cap. This is the way. If it is negative charge density, then I would have written lambda by 4 pi, sorry, not 4 pi, 2 pi epsilon naught minus r cap. Okay, minus r cap. Okay, or here down there will be r obviously. So this will be the thing. Okay, so you guys should read it from the book carefully, and if you don't understand, again you can ask me next class. Okay, I'll just move on to the other application. The next application is, so this is elaborately it is written. You just see that. Now we'll see field due to a uniformly charged infinite plane sheet. Infinite plane sheet. So infinite plane sheet means again sheet. It is sheet. Sheet means area. Infinitely plane sheet actually. Okay. So I have taken this figure here. So infinitely plane sheet means what? Plane means what? It has two dimensions, right? So in this case, infinite means two directions will be infinite. Okay, third direction will not be infinite. Infinitely plane sheet means, suppose you have a very thin, I don't know whether you know OSP sheet, very thin. See, you have your mobile, right? So on the screen there will be skin guard, right? Skin guard. Sometimes you get plastic sheets of skin guard, right? Like skin guard made of plastic sheet. So that kind of plane. So that has, if it is, if you just make two directions longer, other direction shorter, then it is actually infinite plane sheet. Okay. I hope you have not understood. I'll just tell you once again. Plane means what? Plane means you have two dimensions. Okay. This is a plane. Okay, I'll just draw in terms of Cartesian coordinate. You will understand better then. So if this is x, y, z, what is a plane? So this can be a plane. Okay, this can be a plane. Another, this can be a plane. So it is actually containing two dimensions here. So this is a yz plane. This is a y. This is z. This is a y. So this is xy plane, and this is yz plane. Okay, yz plane. And this is similarly, this is xz plane. This is xz plane. So when I say infinite plane, if you take xy plane, so you just increase your x and y infinitely, but this z direction will not be infinite. That means you have a thin sheet. Okay, thin sheet. Infinitely long, infinite plane sheet means you have a very thin but very long in both directions. See, this direction also I can increase infinitely. This direction I can increase infinitely, but the other direction is not infinite. Okay, this is like this. Okay, so this is how it is plane sheet. So I have a plane sheet, vertical plane sheet. You look here. I have a vertical plane sheet. So for which actually, see, the actually yz directions are infinite, but x direction is not infinite. Okay, along x direction. See, if I draw your x y, see x y z planes are drawn here. This is y, and this is x, and this is z. That means look here, uh, this direction and this direction. These are y z directions. These are actually infinitely long, but the x direction, look, this one. This is the x direction. Okay, this is the x direction. This is not infinitely long. So infinite plane sheet means you have two dimensions infinite and other dimension not infinite, that is finite, or maybe very nearly equal to zero. That's why you have a very thin sheet. This is a very thin sheet. If you take a metal plate, thin metal plate, that can act as like a long, like suppose 1 meter, 1 meter, 1 meter this way, another 1 meter this way. So if you have that, that can act as a infinite plane sheet. Compared to our lab experiment would take how much? Would take maybe few centimeter by few centimeter. But if you take some meters, 10 meters, 10 meters, so 10 meters. So this is a obviously this is actually square shape. Anyway, so you understand, right? If you just take even your a single page of your book, also single page of your notebook, is, so that can serve the purpose of your plane sheet. That is a plane sheet. Now you just vertically place your plane sheet. So right hand side and left hand side, if I take that as x axis, you look this x axis side, you have two faces, right? Opposite faces, two opposite faces. So like see in the Gauss's law, we have to calculate the total flux through the Gaussian surface. That means first of all we have to find out the Gauss's law, a Gaussian surface. Then you have to find out the flux, this one E dot ds, and then you have to find out the charge enclosed. Okay, so charge enclosed means, or in other words, if you want to draw the Gaussian surface, you need to know what is the symmetry of the charge density. So in this case, the symmetry of the charge density is what? Which charge density you should take? Nikhil, can you tell me? This is a surface, right? Plane surface. So which charge density we should take? See, it is written already. Surface charge density sigma, okay?
Yes, sir. Surface.
Surface charge density. Yes. So if we want to calculate the total charge on this surface, what I have to do? What I have to do? I have to write sigma into area to get the total charge, right? This is how we can get the total charge. Now look, since it has a planar symmetry, we cannot take any surface like cylinder or sphere. So we have to take a parallelepiped, or sometimes in some books they say Gaussian pillbox. Okay, Gaussian pillbox means you will have cylindrical like a cylindrical Gaussian surface, obviously, but is height is not there. Okay, height is very small. Okay, we will not go to that. What we'll do here, we'll see here they have taken a parallelepiped. Okay, parallelepiped. This is a parallelepiped which has 6 faces. Parallelepiped, you can see that this face, this face, this, like both side, up and down, and right hand side, left hand side. Okay, so there are 6 faces for this. This is called actually parallelepiped. Sorry, parallelepiped. Parallelepiped as a Gaussian surface in this case. So how is the parallelepiped? Actually, this length, this x, like this length is this height. Actually, height of the parallelepiped is not very great. It is very small. If you have a plain sheet of page, how much? If you just take the surface, both the surface, this way and this way, so there is a very little separation, right? So that much length of this uh, parallelepiped has actually. Okay, very so they have very small height, I can say. This is the height. Okay, anyway, so you have taken a parallelepiped as Gaussian surface. You can see this is through this plane sheet. So this is the middle portion. It is through the plane sheet. Through the plane sheet we have drawn a parallelepiped, and it has, see, along the x direction it has 2 faces, 1 and 2 faces along the x direction. Along the y direction there will be 2 faces, opposite faces. Along the z direction there will be 2 opposite faces. If I draw like this, you can see. Okay, just a minute. So if I take, this is x, this is z, and this is y. So see, along the y direction you will have 2 faces, this face and this face, opposite face, right? And along the z direction, this is up and down, this up and down. Okay, and along the x direction another 2 faces, these 2. Okay, opposite faces. So there are 6 faces. Now we have to see along which direction the electric field will be. Along which direction the electric field will be. See, according to the charge distribution, see this plane sheet, it will have electric field by the symmetry of the plane sheet. Actually, the electric field will be, since it is like this, so electric field will be always in this direction. Okay, always in this direction. Understand? By there is symmetry. There will be no electric field along this direction. Do you understand or not? This is by symmetry. Okay,
Yes,
symmetry of
sir.
the plane surface. Okay, so there will be no flux through other surfaces, right, along the y direction and z direction. Will there be any flux? No, right?